we appreciate you guys being here. It means a lot to the students. It really does. It means a lot to me. And I also want to acknowledge other people who have really been a part of why we're here. Obviously, Rod and Nelha, for providing this forum, Tech Bahana. But we also have some sponsors. We are partnering with Pisces, who's our kind of liaison to NASA and the Google Lunar X team. And we also have a partnership with Iolani. We wanted to acknowledge the superintendent of schools, Catherine Madiashi, who selected our school among all the public high schools in Hawaii. And Iolani was selected among all the private schools. And so we're representing that public and private side of the equation. We just want to make sure I didn't miss anybody. So how many of you believe that we're going to be long-term on Mars in, say, 20 years?
I hope so.
30 years?
That's robots.
Not too optimistic. How many think we'll be long-term on the moon in 20 years? Interesting. Because I grew up, in that generation hearing these things. And, well, what you may not realize is that there's been a transition that's been occurring. We are just simply not in the same place we were not too long ago. This transition is really, we're creating a foundation right now. We're creating a foundation for those ideas, for permanent settlement in somewhere like the moon and Mars, okay? For establishing long-term bases to go and penetrate further, okay? To colonization, where I've been hearing all my life, colonize Mars someday, but probably not. It's kind of how I always felt about it. And to actually conveying human populations to other planets, other solar systems, okay? This transition has occurred because, this transition has occurred because of some really remarkable people and some events that have happened recently. Anybody know who that is? You recognize it?
Burt Rutan?
Yeah, that's right. What was his claim to fame recently, last 20 years?
Who around the world was nonstop?
He did a lot of interesting things. But the part that's laying that foundation I'm talking about, Burt Rutan was the first private, his Scale Composites was the first company to privately get a spacecraft or a ship into space. Here's the craft that he was actually able in 2 successive trips within a period of time. And for that, he won the Lunar X Prize, the X Prize for doing that event, which was the inspiration. So we also want to acknowledge, that the X Prize Foundation has been part of this transition. And there's other people. One of my favorite is Elon Musk, who's founded SpaceX. And his sort of passion, enthusiasm, and extraordinary capability set is making things like going to Mars seem plausible. Maybe, in my view, because of people like Elon, going to Mars is inevitable. Okay? If somebody's willing to do the leadership part, I think we can do the technical part. And so because of these different people, we are just in a totally different place than we were 10 years ago. Privatization of spaceflight and all these things is happening. As a result, the private people can be part of this. So, you may not believe it, but I believe it. But tonight, the students are not here to talk about this fantastic future that I'm sort of hinting at. They're here to talk about what is happening right now, okay? Real things, really practical things. If you saw the quote at the beginning from the Earth to the Moon series, they're here to solve the problems one by one over the long course of the endeavor, right, that stand between where we're at now and where we could be, okay? I think that that's amazing, that these kids are actually involved in solving a real problem. But it's not hype. It's the truth, okay? So we're going to have them up and we're going to let them explain that, all right? So let's start with Courtney. I'll pass it to Courtney, Courtney, as a sophomore, remarkably, is the head of our science team. So take it away, Courtney.
She might like PowerPoint.
There you go, Courtney.
Hi, I'm Courtney. I've been in the robotics program. This is my 2nd year, and I'm really excited to be part of the science team. And so what we're looking at is the moon as a launch pad. So one of the problems we're facing is the lunar dust. The There are a lot of really great things about lunar dust, but there are a lot of problems that come along with it too. So for me, I'm going to pass it on to Dean, and he's going to tell you about the history of lunar dust so you can just kind of get like a little more info. And if anybody's talking too much, I got to kick them off because I know we only have 45 minutes, but I'm going to try to keep us all on track. So that's my job today. So here you go with Dean.
Okay, so when and how did the topic of dust come about? Well, it actually starts about 45 years ago in 1969 with the Apollo 11 lunar mission. So this was a space flight that this was a space flight, the first manned space flight this is the first manned space flight to land on the moon. Before the launch, though, NASA was accepting proposals for experiments to be brought to the moon and deployed and to collect data. However, when scientists who had their proposals accepted were actually concerned about the dust. You see, what they were concerned about was that the dust would be kicked up from the exhaust of a lunar module as it left the surface of the moon, and that dust would harm the very sensitive electrical equipment of each experiment. So the solution was pretty simple. They would create detachable covers to protect them from the dust as the lunar module left the surface. But another scientist took it a step further. His name was Brian O'Brien. Now, what he did was he actually invented the DDE, which stands for the dust detector. This is Brian O'Brien. Oh. Long way. There we go. Dr. Brian O'Brien. So what he did was he invented the DDE, which is the dust detector experiment. So what this basically did was it would basically measure the degradation of solar cells caused by the dust. Basically, So the DDE, along with the other experiments, were sent up with the Apollo 11 to the moon and were deployed. And over the years, the DDE would also be taken on with the other Apollo missions of 12, 14, and 15 to collect more data about the dust. So, unfortunately, due to budget issues, the experiments were shut down, but data was stored on these very old tapes. But the thing about these tapes were that they were invented in they were used in the 1950s. So this is what they had to use to actually read the data. Very old, very outdated. But they were able to collect the data, and what they found was very interesting. The properties of dust was very interesting. Is that during the lunar day, dust would actually be more sticky than compared to the dust on the night side of the moon. And it's not sticky like an adhesive, but more of like a charge that it had to it. So, and to go more over that, would be one of these guys.
Hi, thank you so much, Dean. So now that you've learned a little bit about the history, you can see that there's a lot of mystery that comes with lunar dust. And so to teach you more about lunar dust and its properties and what we can use it for, I'm going to bring up Chris, and he's going to talk to you about some of the uses for lunar dust and how it can bring us forward in space exploration. Sure.
All right, thank you for the introduction, Courtney. Good afternoon, everyone. My name is Chris Tabor. I've been on the robotics team for 2 years now, and this year, with our Moonriders project, I'm involved in the science department with Courtney and Nate. So, as Courtney said earlier, the moon's a perfect base of operation. It offers an abundance of resources we can use to colonize and research with. It's the closest object to us. I mean, I'm 100% sure it's the closest object to us that we can get that's outside of our atmosphere, right? So we hope to colonize on it. It's also becoming economically feasible. So as the industry is becoming more privatized with like SpaceX and things, it's also becoming cheaper. So with this, it's no longer just a dream that we have that we can one day colonize the moon. It's becoming a reality. It's becoming an actual thing that we can acquire. It also has 1/6 the gravity and has a lot less atmosphere than Earth. So let's talk about that for a bit. So Apollo 11, the first manned spaceflight to the moon, its rocket was Saturn V. Saturn V, first stage, right? It had 36 million newtons of like thrust at liftoff, right? That's the big countdown. 5, 4, 3, right? Tons of force, just to that's just the first stage, just to barely lift off the ground. And the second stage and the third stage to escape velocity, right? That's just a lot of force. Imagine how much easier it'd be to launch off of the moon. A lot less gravity. It has a billionth the atmosphere of Earth, right? 1 billion. That's just so not much atmosphere, right? But as we like acknowledge this problem of trying to get to the moon, it also comes with issues where we don't like we have a bunch of different ideas on how to get the supplies to the moon, how to colonize on the moon, right? I mean, the first thing you think is, why don't we just ship everything to the moon? Just fly it up there? No. That costs so much money. It is so much weight and so much force to get all that stuff to the moon. That's not the options we go with. So we're going to go with what is called an ISRU, an additive manufacturing solution. ISRU is in situ resource utilization. That's what the Polynesians did. They don't take everything they want to colonize to the place. No, they get there and they use the resources available to colonize land. They use what's there as the catalyst to build and to thrive off of, right? So we plan to do this with the moon. So the idea is that we're going to send 3D printers. These 3D printers are specialized in using the lunar dust as the base material to print our structures, print our tools, print our equipment. So rather than just like sending this building up, right? No. What if we just 3D print the walls, we 3D print the ceiling, everything. We use the dust as the base material and just make it on the moon. A lot cheaper, a lot better. And there's a lot of dust. I don't know if you know that or not, but there's a lot of dust. And the dust on the lunar surface is really good for this 3D printing. A 3D printer generally requires a very fine material, and also has to be carbon-based. The dust is both of those things. It's a really fine powder, right? It might be abrasive, but it's really fine, and it's carbon-based, so it's a really good material when mixed with some other things. You can just start printing structures. It's amazing, right? We've all seen 3D printers, yeah? So, for example here, Washington State University researchers have already successfully 3D printed these little structures. They may not look like much, but this was made using the lunar dust, something similar to it, right? And these structures are solid. They don't have any dents in them. They don't have any cracks. They don't have any gaps. These are solid structures. So it may be a very small step. It's the first step that's spearheading the effort to colonize the moon and to make it a reality. So, as good as this dust may sound, it also has some negative downsides. It's very abrasive in its properties. It gets stuck to the suits. We don't know what happens. I mean, what happens if you breathe it in? It could turn into alien. We don't know. So go over a bit more about that. I'm going to hand it off to Courtney. Thank you for doing my slides.
So I'm going to talk to you more about the electrostatic properties of the lunar dust. So what's really interesting about the dust is it has important uses, and we can use it to print buildings and for 3D printing, but it also comes with a lot of problems. And a lot of these have to do with the charge of the dust. So I'm going to talk to you a little bit about that. So you can see on the light side of the moon, the dust is positive, and that's because of the lack of atmosphere. The sun's radiation is just hitting the dust and it's ionizing it. So you get all these positive particles, and what's happening is that the repulsion between the positive charges is making the lunar dust levitate. So you can see that can have a lot of problems, especially because it's really adhesive. So if you're walking up there, a lot of the things that the astronauts saw is that the dust was sticking to their suits. And you can see that throughout the day, as the sun comes more over the lunar surface, that it's becoming stickier and that the charge is getting greater, and you're just being stuck with a bunch of dust, and it's not good. And it can get in your machines and your robots, and it's not the best thing. But you can see on the dark side of the moon, you get these plasma coming in with these solar winds. And so what's happening is all the ions that the plasma is bringing, all their electrons are hopping onto the lunar dust, and it's making it negatively charged, which also causes this levitation effect because of the repulsion. But my favorite thing is in the middle, where you have this plume of dust coming up. So what's happening is the positive and negative charges are coming together, and they're creating an electric field right at the sunrise and sunset. And so the dust particles are being kicked up by the electric field and going over, and they're hitting their vertexes, and then gravity is bringing them down, and then they're hitting the electric field, and they're coming back up again. So I think that's super interesting. And you can see that kind of connects to our history and the mystery, because the Apollo astronauts saw this glow on the side of the moon, and they're like, what's that? And all these scientists were confused because the moon has a really, really, really thin atmosphere, and so that's not expected. But what you can see here is that the dust is being like launched and plumed so high that when the sun shines through it, it's making this kind of glow. So it's scattering the light, which I think is really interesting. So here's a blow up of a piece of dust. So you can see here that it looks really sharp, and that's because it's melted and that it's like broken up. So it's kind of like glass. So you can imagine trying to get this stuff off. It's really, you want to be really careful. So if you get dust stuck on your suit and you want to shake it off, or you want to just use your arms to just pull it off, and you're just gonna go like that, what's gonna happen is it's very abrasive and very sharp, so it's gonna cut into your suit. And so they've been noticing that it's been wearing a lot of the suits down. So that's something really interesting and a problem that we really need to solve. And one of the methods that we can use to solve this is through the EDS. And so I'm going to bring Caleb up, and he's going to talk more about this.
Hello, my name is Caleb Bishop. I'm a junior. I've been on the robotics team for just over 2 years. The solution that is primarily being looked at is called the electrodynamic dust shield. I'm going to start off by talking a little bit about the history of this device. It first appeared in a paper by an employee at NASA in 1967 who was researching. They were thinking about possible ways to get rid of this dust problem. And then a man named Shinichi Masuda at the University of Tokyo started researching a very similar device, but it wasn't for the same exact reasons. He was researching pollution filters, which is similar because the smog particles are charged just like the lunar dust. So a similar device can get rid of those particles. He wasn't very interested in space, and he started researching other things. So then Dr. Carlos Cali, who founded the Electrostatics and Surface Physics Laboratory at Kennedy Space Center, teamed up with the University of Arkansas at Little Rock, and they won a NASA research agreement to continue developing his device for their own reasons. And for 4 years, they were researching dust mitigation of the dust on Mars for solar panels, because the dust was getting on the solar panels and reducing the efficiency. After that grant ended, they shifted focus towards, that was my Mars picture and Mars solar panels. After that grant ended, they shifted their focus towards the moon and the dust on the moon, which you've just heard a lot about. Now I'm going to talk about how this device actually works. Let's see. So the EDS, it basically creates a ripple wave like this going outward from the center of electric fields that interacts with the charge of the particles and pushes them outward from the center. So there's 3 electrodes, and this is a picture of the EDS. There's 3 electrodes in this spiral configuration, and they're given different voltages, so you get a potential difference from one electrode to the next, and it creates an electric field going outwards. So obviously, charged particles can just get a basic, Lorentz force, Q equals, or F equals QE, just interacting. The charged particle will interact with the electric field. But what's not quite as obvious is that uncharged particles, the EDS is also effective in the mitigation of uncharged particles. What the EDS does is it takes advantage of the polarities of the particles. And if a particle doesn't have a dipole, the electric field can induce a dipole in the particle, as you can see here. So once the particle has a dipole, that dipole will interact with the electric field, and it will be given a force, will be pushed off of the EDS. So particles that are more polarizable compared to their surroundings will be pushed towards the regions that have a higher electric field.
You went backwards on this.
I know, that was intentional. And particles that are less polarizable will be pushed towards regions with less electric fields, so they'll all just be pushed away from the center. So here's, this is that picture. Here's a more polarizable particle, and it's being given a dipole from the electric field, and it's being pushed off that way. So the way that this works
is that there's the 3 electrodes. There's the white electrode, which is going, this is just a cross-section of the spiral. Say the red one is given a higher voltage, so you have this bigger potential difference, and they just alternate from 1 to 2 to 3, the higher voltages, so you create a wave of force, a wave of potential difference across, so the electric field is going across. So obviously this is a very delicate balance, because the thing is like this along across. So I'm going to talk a little bit about the testing that they did to fine-tune this device to get it to work properly. This is a little shaker that they have. It's obviously very complicated just to drop dust. It's because they're trying to get very accurate amounts of dust on the thing. Here's some data that they got. This is the removal efficiency, how effectively it can remove the dust with the particle size. And then these are 4 different values of the spacing in millimeters between the electrodes on the EDS. So you can see that they're all working pretty similarly, but once they passed this certain point, the EDS had a lot of trouble removing the bigger particles. And here's a graph of the voltage reading of a solar panel and how the dust is affecting how much voltage the solar panel is getting, how effective it's working. And this is over time. So they put the dust on it here, and obviously it loses a ton of efficiency because the solar isn't getting through to the solar panel. And then here they turn on the EDS. And these again are the distances between the electrodes. So you can see that after the EDS is turned on, most of them are brought up very close to their original values because the dust is getting removed. Giving it back to Courtney now.
Great, thank you, Caleb. Next, we're going to bring up Ben, and he's going to talk to you a little bit about how we are doing our wiring and our control systems for this EDS. Thank you, Ben.
Hello again, my name is Ben, and along with Caleb and myself, we will be heading up the control systems team, I suppose, for this project. And what that means is we're going to be handling the programming of the EDS, the electronic dust shield, along with most of the rest of the rover. Now, we decided to go with LabVIEW for our programming language. We decided to go with this language based on kind of its understandability of it's a graphic language opposed to like a text-based language, which means that it has a visual flow of information from your blocks to your destination. Another thing is you have a really understandable interface up front with your graphic organizers, such as a temperature thermometer, side by side with the program controlling it. Anyway, so let's see. Other reasons we decided to go with LabVIEW is, aside from the visibility of the information flow to the destination, is the direct link and controllability from the front panel to the block diagram, where you can control it directly from this panel to this panel. And now, since we don't have the electronics for the lander quite yet, we decided to go with programming this year's FRC robot with it. And so we have just different codes we can use to program motor in this case. So we have at least that as a jump pad, sort of, to launch our kind of experimentation with LabVIEW and just get a good feel with it until we have an opportunity to work with electronics.
Great, thank you, Ben. So now that you know a little bit more about the EDS and LabVIEW, we're going to bring on Josiah, and he's going to tell you about how it would be implemented onto a spacecraft. So here we go, and here's Josiah.
Alright, so we know there's a problem, it's dust, and we know that there's a solution, it's the EDS. And we know that there's tests that have been done on the EDS here on Earth. We know that, it is effective in removing dust, and that, it improves the efficiency of our solar panels and our cameras. But the tests that have been done here don't exactly measure up to what it would be like on the moon. And so the objective of our whole project is to see if we can actually test it on the moon. And so there are various conditions that we have to meet, and one of those being that weight is a really big problem. As you heard before, we don't want to carry things all the way up to the moon because it's really expensive. And there's also a limited space. So we're trying to implement the EDS system on a lander that will be on the moon sometime in the next year or so. And so we're trying to figure out what would be a good position for an EDS on a lander that might land there. And so in testing the EDS, we're going to have to try to figure out how the dust will be dispersed across the surface and how we want it to actually be able to measure that effectively. How much dust is there on the EDS before and how much is there on there afterwards. And so we've come up with a number of solutions, some of them being very interesting, such as using like a radioactive element and then having the dust absorb the radiation and then having a Geiger counter count that, because it can be pretty very precise in the amount of radiation that it is able to read, and so the amount of radiation that's absorbed kind of correlates to how much dust is on there. Or we could give it a little bit of heat and see how much dust is heated and then compare that to the surface temperature of the EDS. Or we could just use the camera itself and kind of like get a view of the surface and see if we're making a difference. And so all of these different conditions have to be accounted for when we try to figure out what the best placement would be on a possible lander that would be on the moon. And so with that, we're trying to figure out, well, here, let me zoom out a little bit more. In order to test the EDS, there has to be dust on it, right? There's not really much, we haven't really found out that there's much ways to get it onto there, except for by way of the engines themselves kind of like dispersing the dust that's below it and it just kind of like settling on top. But it's kind of hard to test that on the Earth because on the moon it's basically a vacuum, and on the Earth there's an atmosphere. And so when you're trying to test it, if you put it in a vacuum and then you have the engines give a burst of fuel, oh my gosh, it's not a vacuum anymore. And the only things that are capable of doing that, the only vacuum chambers that are big enough, are very hard to get access to. And so, it's kind of hard to test these things and get any fidelity out of them. And so we're trying to figure out ways to actually test this and see if our proposed solution would have any viability on the moon. And so one of the ways that we're thinking about doing that is through simulations. And we try to make the simulation as precise as possible by giving it Earth-based runs and then tuning it, and then you kind of extrapolate that to the moon. And so with that, I'll hand this off to Courtney again.
All right, thank you, Josiah. So he was able to talk a little bit about where we were thinking of putting an EDS for a possible lander. So one of the things that really got us into this project was our fabrication team. And so I'm going to bring up Zach, and he's going to talk to you a little bit about fabrication and what he's learned from that. Thank you, Zach.
Okay, so I'm Zach, and I'm currently the head welder for this project, and I'm heading up fabrication. So most of the people here have been working on fabrication. I guess I'll name them later. So basically, what we're trying to do is we're trying to brainstorm and create what might be a lander that could land on the moon. And we are going to do this so that we can test the EDS. So we've been looking at positioning for the EDS on the lander, and one of the prime spots has been on the leg because it's going to be getting a lot of dust. So basically, when space-grade mechanisms are built, they're built by professionals who are getting paid lots of money to do it, and they're working in multi-million-dollar shops. We're just a robotics team, and we're at a public high school, and we're trying our best. So we created a CAD for this lander, and the first thing that we started to work on was the hood of the lander. So the hood of the lander is this top piece, and this would hold the electronics. So the first thing we did was we cut out a large hexagonal plate, and we surrounded it by trapezoids, as you can see in the exploded view, and we got that all welded together, and this is where we would house our electronics. So to house the electronics, we made this lower plate, and so this fit on the bottom of the hood, and we have the large rectangle cut out of the center so that we can actually house everything in the hood. The next thing we worked on were the walls of the lander. So we actually did it in two separate parts. Each side is independent from each other, and we did that because we need to fit two large oxygen tanks here and here on the lander. And then that's part of the propulsion system, and there's hydrogen tanks that sit underneath in that extra area. The main central area is the payload. So we created the walls to basically encompass the payload and also support the middle frame that would be the base for the payload. And we're currently working on the leg fabrication. And so here's the thing about robotics. We don't exactly have the tools to make a beautifully curved like space foot for our landers. So we thought about it and we engineered a little bit, and we got frying pans, and they work amazingly. So we've been working a lot on this, spending a lot of time on this. Actually, for fabrication, one thing that we've been trying this year is using jigs. We've never really done that in the past, but they're extremely useful. This is the jig for the side walls. It would fit in like so, and it can all get welded together. And so I guess I'll tell who's been working on the project. So I've been working on the welding, and we have Josiah, who has head of design, has been helping me a lot, basically making sure everything fits together and that I'm doing stuff right. We have Caleb, who has been doing a lot of the cutting, and Ben, who's been drilling the holes, which you can't see, but these three pieces are separate, and they're held together by bolts. We have Amy, who's been doing the marking, which is much harder than it sounds, to create these super precise markings on these giant sheets of aluminum. But we've been having a lot of fun with it, and yeah.
Alright, thank you, Zach. So you can see that we're kind of having this huge nerd fest with this project. So, you know, when you have a nerd fest and you're all together and you're nerding out and you get all these cool ideas, and then you need to share them. And so that's what we're looking at. We're looking at sharing our ideas with the community, and we're going to bring up Kyla to talk more about that, on how we're planning on sharing our little nerd fest so we can spread it across, hopefully, the United States. Here you go, Kyla. Thank you.
So through our dedication, through our design, and through our research on this project, we really want to share what we're doing with our community. So what we have here is our Kealakehe Robotics website. We've created a new GLXP tab where you can see what we're doing. So basically we have a science article page, and when you click on that, you can see a list of a bunch of articles we have about the science research we've been doing. You can see Courtney right here has an article on Apollo 9. So if we click on Apollo 9, you can see her whole article on all the research she's been doing for Apollo 9. So if you really want to learn more about this project, then you can go on our website and read these articles about all the research we've been doing. It's also a great way to really document this whole thing we've been doing. And so we also have our weekly updates. So on our weekly updates, we keep blogs. This is an example of one of our blogs. It's talking about how Josiah and Zach they have the sheet of aluminum that came in, they're marking, cutting, and welding tonight. And then we have some pictures. It's a fun little one right there. They're all inside the room. And now I'm going to show you an example of a vlog.
Okay, so it seems we're having some technical difficulties. So back to the Prezi. Thank
besides vlogs, which you can look on our website, kealakeherobotics.org/GLXP. We'll have all of our vlogs on there. We'll be putting one up every week, so you can really check on our progress and see how we're doing. We'll tell you a little about it. So you learn something, we share it with you. And then we have our student profiles. So besides the seniors, we have everyone who's working on GLXP on our website. And then you can click on, let's say, me, and you can see our profiles and all about ourselves, how we got into robotics, how we got into this project, and so on. So that's our website, so you can go check it out.
Alright, thank you, Kyla. So we get involved in the community and we're trying to spread awareness of our program through our website. But not only do we use our website, we like to host outreach events. So Amy's going to be here to talk to you more about our outreach events.
Alright, so through GLXP, we really want to establish this relationship with Pisces. We live on the Big Island, and because of the geochemistry of the dust being similar to the moon, we're able to have all of these research facilities around us that students should be able to interact with. And through this project, we really hope that we can make these links and we can establish these relationships with the personnel at Pisces and the other organizations that we're working with throughout this project. So we've already started implementing, so all these kids in our STEM camps and our other outreach events, we have talking about these kind of like a kid version of this presentation that we just gave to you guys. And we really want to make sure that these kids know that there's these resources out there and they don't have to fly thousands of miles to the mainland to work at a telescope somewhere over there. We have these telescopes up here. We have these research facilities here, and they can work in a lot of different types of space, astronomy, and aeronautics if they really want to here as well.
All right, thank you so much. We're going to bring up Mr. Brown for some closing statements.
So yeah, thank you guys. I think it's a fine job, and I kind of want to. They were on a very muted version of the explanation because a lot of the stuff that we want to talk about is kind of redacted right now. But I want to encourage everyone to check out this project. There's a lot of other things that are actually going on, and in the next couple of months, we're going to have the opportunity, after some paperwork in the mainland gets signed, to really go into details about how these things will be implemented into some very exciting things over the next couple of years. And we really think that this is going to be a long-term link between the Big Island of Hawaii and the international space-seeking community. As the student said, the geochemistry is very unique, and we feel very honored that of all the schools that we were selected to have this opportunity over the next few years to develop some original research that has the potential to fly and also inform permanently our understanding of this. If such things were to develop, for instance, and these experiments were to continue forward, this would be the very first high school experiment ever performed on the surface of the moon or any non-Earth-based thing. Several experiments have gone to space. However, we're very excited about some of the potentials and some of the other things that we're going to be able to talk about in a couple of months. So thank you all for your time, and now the students are all available for some questions.
First one, just can you talk a little bit more about why it's all hush hush? I mean, like, what's the rationale behind it being hush hush? You don't have to say what you can't say, but
what you're talking about.
Well,
I would love to talk about everything. As you might imagine,
I mean, NASA's a public entity, right? It's a government agency. It's our tax dollars. So, just curious.
Projects all have different levels of publicity, and I think one of the biggest reasons is because the offices have asked for a coordinated rollout of the actual projects that this research might be associated with. And so there have been 2 scheduled dates in which that rollout would happen before this. We were hoping that would happen after this. And those both got moved because of the approval process for these types of projects. For instance, for those of you that are familiar with ITAR, things like this have to go through ITAR approval. That's a decently long process, right? Because this could be dealing with, potentially something like this could be dealing with things that might be interest, that people might feel have military applications. So what information is being passed to whom? Is everyone U.S. citizens? How is all of that occurring, and is all of that legal and defensible? And so a lot of people have to say that they think it is. And we believe everyone has, but we're still waiting on the actual rollout.
Well, I don't know if you can answer this, but your lander, is that like, did you guys design that? Are you guys designing that, or like were you told like that was like just build this and then find something that fits on this? Or,
So,
I'm just not sure. Like,
well, we've made multiple modifications to it, but much of it was publicly available
okay.
through
So this is like
Kealakehe
standard
sources.
lunar
Yeah, and then we just kind of added a bunch of our own. We actually have like completely recatted the whole thing because this came from basically an image, and we just like, and there it is.
Okay.
So,
Something that like has to be
That's only you
and
design.
just
all the GLXP teams have websites which you can go and get lots of information from, and we access that information and made some decisions based on that and things that we were seeing in the trends for the 2015 launches to kind of design this to inform. So this, what we can say is this vehicle will certainly be tested at the Mauna Kea test site, right, with systems like those that were described for environmental mitigation.
so you're designing the lander and the device?
Yeah, and then integrating the device into the placement of the device will be exceptionally important, which Josiah was talking about. It's already known that the device works exceptionally well on Earth, and there's published papers on that. There is no current knowledge on if it would work on the Moon or Mars. And so placement where you could get a very accurate and well-measured experiment is going to be crucial.
Go ahead. What was the genesis of this project? Did you guys compete for a solicitation? And was it through NASA?
Well, some of you actually may remember Pisces' presentation here at Nelhaw just earlier this year. So this project has been, Rob Kelso has been very interested in this project for many years. And my understanding is that there was actually a desire to get 3 entities working independently on this. The cultural schools, the Kamehameha schools, a private school and a public school, and the chief officers at each of those were contacted to develop recommendations for that. And right now we're looking at Kealakehe School representing the private side, and then Superintendent Matayoshi actually personally selected us.
And the word Moonriders, is that your project, or is that?
So Moonriders is the official title of this entire project with all of the partners, and this is a logo associated with that. And so research, investigating dust expulsion and removal system. So all of the entities working on this project and any implications for this project as far as launch will be using Moonriders as the code, which obviously is the Kealakehe Moonriders. We're quite pleased with the name. But it was signed up. The sign-off process on color selection, fonts, that's been a very interesting process to learn about as well.
Made suggestions, but no, that's all you could do.
I'm not sure if I got that you got a way to keep the vacuum and low gravity thing simulated. Do you have a way to do that?
So there's currently no way to physically do it. Not that we are capable of, but we're trying to use simulations and to make like a very accurate simulation based on what we're capable of, and then to kind of extrapolate that to what would happen if it was on the lunar surface. And that's basically just to figure out how the dust is going to distribute itself on top of the surface of the EDS in a landing.
Are you going to try to plug your gear into that? Or a specific gear?
So I guess I'd say that terrestrial-based testing and lunar testing would be different as far as how the control systems and the experiments would run. And I think there's several options, and that's going to be the topic of Josiah's paper over the next hurry up time. But There's also zero gravity planes that can do some of this testing, that can recreate moon gravity and conditions.
Or even dropping it from the building or something.
The crane drop. This was designed to be able to be dropped from a crane. So, crane drop in a vacuum. You have some ideas on how to create a 25 by 10 by 8 vacuum that
continuously suck air out because we're going to be
at
blowing
1/6.
air.
We don't have to suck it out of the whole depth.
Yeah, that seems yeah.
Yeah, I have kind of an interest about what's going to happen many years from now. This is a project that's going to go on for maybe the life of the Earth. And just like when an ice skater is spinning and they pull their arms in, they go faster. So same thing, if we were to scoop a bunch of dirt from the equator of the Earth and put it at the poles, then the Earth would spin faster as well. And the moon, if we go up there and start mining that thing and sending stuff to far distances, we're going to affect the orbit of the moon.
I would disagree.
Good. Neither of us will be around to prove it.
Well, I think we will. We've certainly sent tons of stuff up there. I think it's more of a scale issue.
Scale, yeah.
In that every single person in the world could move to Manhattan and jump, and it wouldn't matter at all. It'd be calculatable, but it wouldn't matter. And there would be more natural occurring phenomena like meteorites crashing into it that would have more measurable difference. So I think it would be calculatable, but I guess I'd say I'm not overly concerned about the moon spinning out of orbit. I wish that we had the capacity to do something so profound. I don't think we do.
I think an ice skater pulls maybe 5% of their weight in. And so everybody moving to Manhattan would not be 5% of the weight.
Right, and every single thing I could ever imagine us doing.
Yeah.
Although there might be more people that know more about that, I guess. My initial reaction is I'm not too concerned about it.
Imagine more.
Yeah.
Maybe what we thought about this. I was talking about the difficulty of getting the dust to be in a cloud, in a vacuum, without blowing it up with air or something like that. So I had two thoughts, and maybe you've already considered this. If you put dust on a drum head and hit the drum, dust flies up in the air. So you could do the same thing by hitting the floor with a sledgehammer or an explosion. You get the dust, I would say airborne, except there's no talking about in a vacuum. The other possibility is to attach the dust to the ceiling with an electrostatic plate and then turn the plate off. Maybe you thought of that.
Okay, so I appreciate it, and we're definitely looking for solutions. So the biggest problem with this is that we're trying to figure out how the dust gets distributed based on the landing itself and the air that's coming out of it, or like the fuel, the propulsion that's coming out of it as it's landing. And so it's not a problem of getting the dust actually up. We have to still, simulate or replicate the actual propulsion system that the lander is doing, and with that, you're gonna kill the vacuum.
And one of the other things is it might be nice, let's say, as an experiment like this, were it to, maybe in November of 2015, be on the moon, that you could replicate the experiment. And so finding ways like they do in what Caleb was explaining of getting precise amounts of dust would be exceptionally useful, because you could maybe do it a couple of different ways at a couple of different times. Who was talking about? Dane spoke of the stickiness, right? During the day, as more into the sun, the more charged it gets. So it would be interesting to see what's the effectiveness. Does anyone know how long the lunar day is?
28 days roughly, yeah.
So you have about 14, right, growing temps. So if you could do it 7 days later, right after it's at 7 days to get sticky. Most landings and most of the GLXP teams and other landings, they all happen in the early morning of a lunar day. And so if over time we could look at those effects, in which case we need to get not just dust. We would need to get the day 11 dust onto there. So how do you collect day 11 dust and get it on there, and then see, do you have different effects? So those are all some of the things that would be interesting in research like this.
Is the vacuum on the moon a total vacuum? Is there a loop, like
1 billionth the Earth's sound.
I mean, is there enough to put your blower inside of the vacuum? Not the true vacuum. It would stir stuff all out, kind of outside. Well,
Good. That's something to consider. Yeah. Go. Chris Tabor. Yeah. Chris Tabor will find that answer out for you.
Because, I mean, they've done landings with parachutes, right? That just float it. So, I mean, there's a measurable amount that you can actually use. It'll be very interesting to find out.
So what is the next big hurdle you guys are up against? What's the next step?
In a project like this?
Yeah.
Well, in a project like this, I would imagine that the next big hurdle would certainly be finding accurate placement for a system and then integrating it at some type of weight capacity. So you might imagine that a project like this would need to have some type of weight limit, right? Talking about $1 million a kilogram. So securing shipping funding and then ensuring that your device can get under that shipping funding cost. If you were, per se, to get 500 gram allotments, well, every gram is $1,000, right? So how wonderfully accurate and precise, except still exceptionally strong, can you make casings and electronic systems, right? How can you solder things and have 0 extra? Because 2 grams, I mean, that's $2,000 that you need to go out and secure and funding. Despite the fact that many of these projects, so y'all can all go online and look at SpaceX teams, and if you would like to send something up to the moon in 2015, you can. They'll tell you their payload requirements, their payload locations, when you need to get it to them, and then they'll give you a bill for $5.5 million. And fitting into all of those requirements is, I think, going to be a very interesting challenge. If you were to look up EDS systems, you might see boxes about this large. So that's not going to fly. So that's going to be an interesting thing, Josiah, to engineer at a very precise level, and then integrate very little wire with lots of power.
Okay, so instead of figuring out couldn't you just come up with an anti-static opposite charge? You already know it's going to be daylight. So could you have your gear be negative?
Two?
Repeat that question.
Instead of trying to go through figuring out how everything works, could you just come up with gear that will repel the dust?
Well, there's going to be not just positively, there's going to be all different kinds of charges. There's going to be positively charged particles, negatively charged particles, and a couple different kinds of uncharged particles. So we can't just use a single variable like it has this amount of charge. We know that like the majority of it is going to be some specific way, but the EDS
Depending on the time of day.
Yeah, depending on the time of day. But they wouldn't work for all of the dust. It would just work for a majority of it, and we want to reduce more than just the majority of the dust. We want to get rid of off of others.
Yeah, the fact that the EDS works with uncharged particles is quite remarkable. I mean, Caleb did describe it as being quite fun. Very interesting.
Well, we'd certainly be happy to answer any more questions or talk about the project, but certainly want to respect the time allotment, and we can